In the last few years, artificial intelligence has made leaps so rapid they've begun to feel like science fiction. But behind the hype, there's a quiet revolution happening in how machines learn, especially in the way they process language. Today, we're diving deep into one of the most transformative breakthroughs in modern AI, the emergence of large language models and what makes them tick under the hood. At the heart of every large language model lies a fundamental idea: prediction. These models don't understand language the way humans do. They don't grasp meaning in the philosophical sense. Instead, they learn to predict the next word in a sequence, based on everything that came before. It's not comprehension. It's pattern recognition on a scale we've never seen before. But how do they learn to do this? The answer lies in a massive dataset, often trillions of words scraped from books, websites, scientific papers, and even social media. The model is trained by showing it vast amounts of text, then asking it to predict the next token, whether that's a word, a subword, or even a character. Over time, through billions of iterations, the model adjusts its internal parameters to minimize prediction errors. This is the essence of supervised learning, but on a scale that defies intuition. Now here's where things get interesting: the architecture. Most modern large language models rely on the transformer, first introduced in 2017 by Vaswani and colleagues in a paper titled "Attention is All You Need." This was a turning point. Before transformers, recurrent networks like LSTMs were the standard. They process text sequentially, one word at a time, making them slow and hard to parallelize. Transformers changed everything. Instead of processing text step by step, transformers analyze all words in a sentence simultaneously. They use a mechanism called self-attention, which allows each word to weigh its relationship with every other word in the sequence. So when the model sees the sentence "the cat sat on the mat," it doesn't just process cat after the and sat after cat. Instead, it considers how cat relates to sat, how mat connects to on, and how the at the beginning relates to mat at the end simultaneously. This is done through a series of attention heads, typically 16 to 32 in modern models, each capturing different types of relationships. One head might focus on syntax, another on semantics, another on coreference. For example, in the sentence, "John saw Mary and she smiled," attention heads help the model determine whether she refers to John or Mary. That's not magic, it's math. The model learns to assign higher attention weights to words that are semantically or grammatically linked. The self-attention mechanism computes a weighted sum of values, where the weights come from querying the relevance of each word to the current one. The formula looks like this. Attention Q K V equals softmax, Q K letter 1D40/square root DK V. Where Q is the query, K is the key, V is the value, and DK is the dimensionality of the keys. This might look intimidating, but it's just a way of measuring how much each word should influence the representation of another. After self-attention, the output passes through a feed-forward neural network, two linear layers with array LU activation in between. This layer applies nonlinear transformations to the attention output, allowing the model to learn more complex patterns. This entire block, self-attention followed by feed-forward, is repeated multiple times, forming what's called a transformer block. A typical large model like GPT-3 or Llama has 24 to 96 of these blocks stacked together. Now here's a critical point. These models don't have memory in the traditional sense. They don't store facts like a database. Instead, knowledge is encoded in the weights, tens of billions, sometimes hundreds of billions of parameters. Each parameter is a tiny number that adjusts how information flows through the network. When you ask a model a question, it doesn't retrieve an answer from memory. It generates a response by sampling from a probability distribution over possible next words, based on all the patterns it has learned during training. This is why prompts matter so much. The way you phrase a question shapes the model's internal state. A well-crafted prompt can guide the model to produce coherent, relevant, and even creative outputs. But it also means that models can hallucinate, generate plausible-sounding but false information, because they're not verifying facts against reality. They're just predicting what's likely, given the data they've seen. And that leads to a deeper truth. These models are statistical engines. They're not reasoning. They're not conscious. They don't have beliefs or intentions. They're incredibly sophisticated pattern matchers, trained on the entire written output of human civilization. But despite that, they've unlocked new possibilities. From drafting emails to writing code, from summarizing research papers to generating poetry, their capabilities are expanding rapidly. And the underlying architecture, the transformer, is now the foundation of nearly every major language model. So what's next? Researchers are exploring ways to make models more efficient, more accurate, and more aligned with human values. There's work on retrieval-augmented generation, where models pull facts from external databases to reduce hallucinations. There's research into sparse attention, which reduces computational cost. And there's growing interest in hybrid architectures, combining symbolic reasoning with neural networks to bridge the gap between pattern recognition and logical inference. But no matter where we go, the transformer remains the cornerstone. It's not just a model. It's a paradigm shift in how we think about language, computation, and intelligence. So the next time you ask an AI to write a story or solve a problem, remember, you're not talking to a mind. You're interacting with a vast, intricate web of mathematical relationships, trained on the echoes of human thought. And that, in itself, is one of the most profound achievements in the history of technology.